right. So, um, thank you for coming. The weather is beautiful, so yeah, I wouldn't have blamed you if you guys wanted to just be outside, but we can't take the projector out there, so we have to be inside for the moment. All right, so it's a shorter lecture today because we've sort of been circling this topic for a while. So now it's time to formally introduce it because when we get to deep nets and yeah, basically when we get to deep nets and all the good neural network architectures, transformers, all of that, it's going to be really, really, really annoying to calculate the loss gradients by hand and do all of that, right? So, you know, this being we're engineers, we're supposed to use tools. As much as of a good learning experience it would be to force you guys to implement a transformer without PyTorch or really anything other than NumPy, I'm not that cruel. So we're gonna try to use we're gonna learn some of the advanced tools. So when we get to that point, learning those things won't be so bad. Okay. So so today is just the PyTorch nn.module library. We're just going to go through some examples of what it is, and then of examples of how to use the optimizers it provides, which are very similar to what we've been doing so far. And then just standard recipe / example on sort of a more advanced classification that we talked about last time. So let's go on. So recap, we have a data set with endpoints. We have a model with some learnable parameters theta. So that's a good thing. When you read papers, usually they denote all the learnable parameters, i.e. all the weights, with the term theta, right? This theta is a set of all the weights in the model that can be adjusted. So it's not an input. The inputs can't be adjusted. The inputs are the inputs. The output is just whatever the model spits out based off the slopes and biases that exist in the model that have been trained so far. Okay? So that's theta. So the model we say the model is simply a function of theta that takes in an input x and then outputs a output y. And actually, I want to use t here because I used that for the actual targets that we trained to. And then we, of course, have a loss function. This, by the way, in case you guys were wondering, well, the actual number is the actual thing in LaTeX. This is an actual symbol in LaTeX. It's called ELL. Also, in LaTeX, this is just like sort of a LaTeX device. There's a set of symbols under the MathCal library, so it gives you sort of fancy letters. It stands for math calligraphy, so that's how you get the sort of fancy L. I don't think this is standard. The L is standard for the loss function, although it's common. But we say the loss function is a particular function that takes in a model consisting of parameters and optimizes it given some targets. There we go. That's what I wanted. So the learning algorithm to update the parameter values using the loss function, the gradient descent, is called the optimizer. Okay? So we have three different things going on. We have a model, we have a loss function, and we have a particular optimizer. And those are really the only three things we need to define. The data set, presuming the data set is already defined and formatted for us, to get a actual neural network model. So, for example, let me put this on a separate slide. I wish they allowed you to have have different sort of slide types for different monitors because, like, as a notebook, that looks good as a fragment. But anyway, well, on my screens at home, it looks good as a fragment, but then when you come here, the resolution's lower, and that's why it throws me. Anyway, so again, in logistic regression that we talked about last time, we have a data set D. I'll change this later, which is, well, I'll change it now. Something targets consisting of ones and zeros. So I should say, really, this is binary logistic regression. And then we have a model, F0, or f of theta, where f of theta is simply the model trying to output the probability that the model outputs something equal to 1. That is the probability that the targets of I is equal to 1. And in the case of the logistic regression, we use the sigmoid function, which again is 1 over 1 plus e to that linear parametric model. And the parameters theta of WB are simply any real number. Okay? Are elements of real. Why is it real 4? Why did I do real 4? I'm going to do that. So the loss function may be, okay, so last time we talked about multiple loss functions. The loss function could be either binary cross entropy, as I put on the slide. Why did we not use mean squared loss for logistic regression? Remembers? Yeah, please, man.
It runs into that issue where if it's super far off, because it's sinusoidal, or sorry, because it's sigmoid.
Yeah, sigmoid, yeah.
The gradient ends up being mean 0, and so it doesn't accept.
Oh, perfect. So yeah, exactly right. So we ran with logistic regression. We ran into the issue where we had something like this. We had a sigmoidal function for the loss. So the issue is that, you know, if the model guesses correctly, I mean, the loss is very close to 0, so that's good. On the other hand, if the model guesses incorrectly, the loss is close to 1. But worse, the gradient of the loss is close to 0. So it makes optimization difficult. Not impossible, but very difficult and not ideal, right? So that's why we use the cross entropy, because it gives that little hinge loss. That little hinge loss where if you're correct, you have pretty much a loss of 0 with a gradient of 0. But if you're not correct, you have a ever increasing loss that increases the further off correct the model is, right? That's what we really want. So, good. So binary cross entropy, we defined it as so. We could define this further with logistic regression, but we don't really need to at the moment. We could keep it like this, and everything will work out just fine. And by the chain rule, we obtain the gradients or the partial derivative with respect to the weights, the gradient or partial derivative with respect to the bias, and use gradient descent with a step size and with some particular step size or a learning rate of alpha. Okay, so that was our formula, and it works pretty well. The only issue is that it was a little tedious to code up, right? So it was a little tedious to code up, so that's why the torch.nn model, the torch.nn library is very useful to us, because it makes things a little easier to code up. So before we get to that, let's just review a little bit about objects and classes. A class, most of you know this from object-oriented programming. Out of curiosity, you guys do object-oriented programming in what, 225, something like that?
A little bit of 220
220.
also.
Do you use Python or do you use C? C++. Okay. All right. Well, so it's mostly the same. Although Python plays a little looser with the idea of classes and inheritance and stuff like that. But you could keep. We're not going to be doing anything too advanced, so you could keep the same idea. So class is a collection of attributes and functions. Attributes are the little actual variables inside the class that define the class. For instance, if you had a class of 0, one of the attributes, i.e. variables, might be radius, something like that, right? And then you have a bunch of functions in that class, which is, again, if you had a class of 0, if you had a class of circle, then a function might be area that returns pi r squared. A function might be circumference that returns 2 pi r, that sort of thing, right? So you have a class, collection of literally variables, attributes, we call them attributes, and functions, and so, or methods, I should say, and the methods are just functions that are specific to the class. And a object is a instance of the class. So same way when you call a function, when you call a function in C, you're creating an instance of that function on the stack in the operating system. Same thing here in coding. When you create an object of a particular class, you are creating a physical thing, right? The class is sort of a map, but then the object is the actual location, the actual physical thing that map describes, the actual particular map, okay? So, so the object is an instance of the class, and separate objects might, the reason for this is because separate objects may have separate functions, right? So again, if we have a object of the class circle, one object of the class circle may have a radius of 1. The other object of the class circle may have a radius of 2. That's why. We want different circles, right? Different physical things. And so unique to Python, not necessarily, I can't remember, C++, did you have self in C++? You had this though, right? Yeah, this. Okay, so the same thing, yeah. I use, it's amazing. I still use Rosetta. Every time I need to use a programming language, I literally put Rosetta code on one screen to just relearn the syntax of that programming language. So, so in Python, you have this self-identifier, which literally tells the function tells the function or whatever that you are referring to yourself. You are referring to a particular value that is in this class, okay? So it's kind of important because without it, the function won't automatically assume, for instance, if you say return pi times radius squared, it won't know you mean the radius that is in this class. You have to say return pi times self.radius squared, okay? That I always found frustrating with Python because you end up with self just everywhere. But to each his own. So using the self keyword, you access the attributes and methods of the particular object with the class definition of the particular object that you are in. Okay, and also you have the init method that is a reserved name for Python classes that is basically the constructor. It just runs when the new object is created. So when you say x equals a circle, x equals a new class circle, then when you create it, that's where the init method comes into play. You could omit it, but typically you want to actually use it to define whatever attribute, to actually put a default value to the attributes you have that you need to define. Okay, so that's just the constructor. All right, that's just a bit of terms that most of you are probably familiar with in general already, even if you're not familiar with the particular names, you'll pick it up. Okay, so the nn.module class is the base class for neural networks. Okay, so for neural networks and more broadly, the trainable models that are found in the torch.nn package. So a NN module is simply a function. It's simply implementing a common function that people use often in machine learning. This is like ReLU, rectified linear unit, right? Or sigmoid. These functions, they call them modules in torch.nn. Okay, and there are two methods, and the two methods that you should pretty much always implement. I don't think you have to implement them. I want to check on this. But you pretty much do always implement them. Are the constructor, which is you want to, when you create a neural network, you want to actually tell it what functions go into the network, and the forward class. You want to actually say the calculation, right? You want to say what the calculation is. So again, init mention specifies a constructor, and of course you guys know about inheritance. So when init is called, the first call is the super.init, which is specific to the NN module class, which you guys will almost never, you guys probably don't need to worry about. This is useful if you're actually making like a unique type of neural network. Then you can modify that. But when you call init, you call a constructor where you define the neural network, and then you also implement the forward method, which implements how the model actually processes the input data for the forward pass. And as we know, once we define the forward pass, then then Torch itself constructs a computation graph that will be used to calculate the backward pass as well. Right? That's the beauty of Torch. You only need to implement the network in the forward motion, and then it'll take care of everything that you need to do when you do back propagation. Okay? So for an example, we did polynomial fitting 3 lectures ago. So let's try to do that again. Third order polynomial regression. And in this case, we have f is equal to a times x cubed, b times x squared, cx, and d. And so the trainable parameters are a, b, c, and d. There is one input, right? This x is the same. So there is one input x and one output. And so trainable parameters a, b, and c. So we could write the corresponding NN module class as follows. Simply, we have a NN module that is third order polynomial. We write this NN module to inherit the functions from the NN module class. And then we specify the learnable parameters. So remember how before we basically said the weight is equal to a torch.tensor, and then it is equal to torch.tensor, and also we specified that requires gradient is equal to true, because we wanted Torch to keep track of the particular we wanted Torch to keep track of the computation graph starting from those weights. Well, things become easier. So instead of doing that, we could simply specify some attributes and say simply that the attributes are, we first call the constructor of the NN module to initialize sort of the NN module, and then we could simply say A, B, C, and D are attributes of this class, okay? Or parameters, I should say, parameters. So that makes things a lot simpler. And also, we didn't necessarily need to make A, B, C, and D separate. We could have simply put 4 here instead of rand 1, but this is just for visual clarity. And so all that we're doing in the init is basically we're basically initializing the torch.nn constructor. This allows us to get access to all the good methods that are in torch.nn, and there are a lot of them, basically optimizers and stuff, which we'll see in a moment. And we say what the parameters for this model are. And then finally, we need to tell how those parameters are connected to each other and to the input. And so we have a forward pass. And so forward is a reserved name in PyTorch that basically specifies that the output is simply equal to the parameter, the attribute, self.a times x cubed, plus self.b, the attribute self.b, times x squared, and so on. Okay? So, and then we, of course, return f. So this is our whole model. Okay, not too bad. Um, and so this is our class. This is, I should say, this is our model. That is the third order polynomial model. So we want to initialize a new instance of that class, a new object. So we simply, you guys are used to this, we simply say variable is equal to whatever the class is. And then you have something, and then you could list out the attributes. And in fact, here we know that each of the parameters is initialized to some random number between 0 and 1. And in fact, you see print A, B, C, and D are all random numbers initialized to between 0 and 1. And the prediction is simply equal to the model times the input. Okay? So the important thing here is that you don't have to specify forward. When you simply pass a input to model, it assumes that you simply are calling the forward function there. And so that makes things kind of nice. It makes things clean in the coding sense, that all you need to do to actually get the output for a particular model is simply say that model input. Okay. Yeah. Also, so it's never going to harm you. One thing, it's never going to harm you to put self into these definitions. You don't necessarily have to. You don't necessarily have to pass in self into the actual methods in the class. But if you don't pass in self into the method, then you won't actually be able to call on attributes inside the class. Okay? So I've never been happy with this. I don't think C does this, right? C, that you don't have to keep passing in the pointer to the, this, right? Yeah, this is one of the weirder, like this and the whole white space delimiting is some of the weirder choices of Python. But they do this because, in theory, they do this because of security. And so if you don't pass in self, then you could still have functions that are just methods that you could call that are included in the class, but not necessarily have access to the class attributes. And so I guess it's a security issue. I've never seen the point of it, but you know, every language has its own idiosyncrasies. We just have to live with it.
Kind of like private versus public, right?
Yeah, it is. So why don't you just do that? It's very frustrating. Man, I really wish another scripting language other than Python, like one. Yeah, although I can't think of many scripting languages. Yeah, I can't think of anything off the top of my head. Anyway, that's a whole rant for another day. All right, important things to note. Important things to know. There we go. Don't make this a fragment. Make this a slide. There we go. Self parameter is needed. Oh, I just said when is self not needed? Basically, if you want to have a method in the object that doesn't have access to its own attributes, you can use the self parameter. There's some other like little edge cases where you might not include the self parameter, but almost always people include the self parameter. So I just make it part of the functions whenever I'm writing this. I just put self everywhere. And then the model parameters are specified using the parameter class. Yep, we covered that. And automatically collects all learning parameters. Oh, and yeah, so one of the nice things about the torch.nn library is that you can list out all the learnable parameters by simply saying model.parameters, and it will list out all the possible parameters. So for instance here, we just print out the learning parameters and we get the 4 learning parameters we see. Okay? Yeah. And I know this isn't how computer programming works, but I really do wish they gave you the names of that. But they usually don't. I mean, I don't know any language that would do that. That should be a feature of some language. Okay, so let's work through an example. Well, I mean, the polynomial case was good, but let's just work through another example, namely the logistic regression module. So again, we have a particular logistic regression that has a probability that a target is equal to 1, given by 1 over 1 plus e to the negative linear expression. Okay? So we could write the code as follows. Let's do that. We have a particular weight, and we're assuming a single input x, 1 or more. Let's assume 1 or more over here. So we simply say that we simply define a dimensionality to the input, and in this case I'm saying n is equal to 1. So assuming that we have n inputs, then we want to define a sigmoidal function that has n weights and a bias, right? So that's what we do here. When we want to create an object, we simply pass in a parameter that is the number of inputs n. So we pass in a parameter, number of inputs n, and into the init function, into the class constructor, we simply call the torch.nn constructor just to get the methods, all the nice little methods that we need, especially parameter. And then we simply say that the w parameter is simply a parameter that is equal to the number that is a vector equal of size, a vector of ones of size n. Okay? And then we want a bias, which is also a parameter, but in this case, it's simply a vector of size 1. And we initialize it to 0. We could use rand, we could use whatever. But we'll just do it this way. And then we want to define a forward function. We want to define what the actual model does, right? In this case, it's fairly obvious, but sometimes it could be less obvious. So when we define forward, we simply say that the forward pass is equal to that's not needed, that was debugging. It's simply the forward pass is equal to 1 over 1 plus torch 1 plus the exponential to the negative self.w times x plus self.b. Okay? And so this is, again, remember, this is the vector multiply that we need, right? This is a matrix multiply, vector multiply, same thing. So that everything gets summed together. All the wx's get summed together. And yeah, and everything works like that. So when we have when we create an object, in this case we're creating an object of size 1. We're saying that there's only one input. We simply pass in 1 to the logistic regression class, create a new object. We say the input is some random number, and the output is the actual function. The output is the actual neural network, which is simply this forward pass. So the output y is simply when we say output, when we call the class and then pass in an input, it simply matches it to this forward pass function. Okay, and then I just included a bit of code to plot this to plot the logistic function we just defined. So again, I'm just doing x values are equal to the linear spacing between -5 and 5, and then I'm just passing in the x values into the model, and then getting the y values out, and then getting the image. Okay. So one interesting thing, is that the x values, let's say I want it, why did I do that? Why did I do .view? So let me print out, this might be helpful for you in the future. So I'm going to belabor this point a little bit. I'm going to print out the x values there. And I'm going to print out the x values here. So initial x values is simply a tensor array. And x values is, again, oh, I was like, what's going on? Actually, I'm going to print out x values at 0, and then x values, because that's what I'm doing. Okay? So one little thing is that the reason I did the view there is that when I refer to a particular value in the tensor, it gives me a scalar object, right? That makes sense. I have an array. I defined an array. I said I want the 0th element of the array. I get a scalar object. That's all well and good. But if I, for instance, want a if I, for instance, want to pass this in to this function does a matrix multiply here. Okay? It does a matrix multiply, and so if the dimensions don't match, then it will complain. So because you're doing a scalar times a vector here, PyTorch did not like it. So I had to basically reshape this scalar into a vector, and then PyTorch would accept it into the matrix multiply. Okay, so nice little trick here. That's a nice little trick that you could use in the future when you want to do a matrix multiply, but the PyTorch is balking at it because it doesn't like scalars to work with. It doesn't like using scalars with the matrix functions. Just use the dot view parameter. And in this case, I made it a two-dimensional vector where the last dimension is equal to 1 to match the size of W there. Okay, makes sense? Nice little trick. You guys will see it eventually. So you guys will get that. You guys will get such errors eventually. So when you do, hopefully you'll remember this little slide. Okay, so we have the ability to define a neural network. So what do we need next? We need a loss function, right? We need to describe how we want to optimize the neural network, what the objective is, right? That's why it's also referred to as an objective function. We need to tell the network, actually we need to tell the optimizer, my apologies. We need to tell the optimizer how to change the parameters to get the desired output, to get our desired output. So with loss functions, we could define our own, as we have done many times before. But the nice thing about Torch is that you have a lot of different loss functions that are implemented as classes. Okay, so for instance, NN, that mean squared error loss, is simply the y minus t squared, the sum of that. That's NN dot mean squared error. I mean, you could do that yourself. You could define the loss function yourself, or you could use this nice little function. Get on with your life. Cross entropy, all those other good functions are there as well. I hopefully have been consistent with this. So one of the reasons I usually use the term t instead of saying y to describe the output of the data set, to describe the labels of the data set, is because we have the name model, we have the inputs are named input, and usually the ground truths, i.e. the actual labels in the data sets, those are named targets, okay? The labels in the data sets are the ground truths, and usually they're called targets. That's what we want our model match, right? Makes sense. And then, of course, the loss function object is named the criterion, or not of course, but it is referred to that criterion because it's simply, that's how we want to optimize our model. That's the criteria we have for improving our model, for training it, i.e. the criterion. that we'll use to train our model. That's what we refer to as the loss function. So it could be something very standard, mean squared error loss, binary cross entropy, or it could be something completely complex, something that you're doing that you completely made up yourself. And so we define the loss function. We define the predictions as the model inputs. This is actual what the model gives out, right? For a particular set of parameters. And so the criterion is simply the loss function given what the model is currently giving out and what the target, what the model should be giving out. And then this will be used to backpropagate that loss function, as we've seen before. So let's looking back, we have torch.nn, we have a particular x inputs, some zeros, we have a particular y, we have a particular y, oh sorry, we have a particular, in this case x would be the predictions, in this case I'm going to rewrite this actually, predictions, targets, and so this would be predictions, what the hell was that? Okay. There you go. Okay, hopefully that makes the code more readable. I'll update it. I'll update the website when I get back. So we have a set of criteria functions. So for instance, mean squared error loss, we have many different options for mean squared error loss. And so we could either have the loss be the mean of all the data points, of all the little losses. It could be the sum of all the little losses. The sum is what we've used pretty much constantly throughout this whole thing. Or it could be none. You could just get the loss for each particular data point. So for each of these points, we print out if, for instance, the mean squared error loss, we want the mean of all of that. The difference, the mean difference between 0 and 1 for 4 values is, of course, 1. If we want the sum loss between 4 zeros and 4 ones, the difference is, of course, 4. Or if we want each particular loss, the difference is 1 for each particular data point. Okay, makes sense? So that's the useful thing about using these loss functions that are predefined in the nn.functional library, in the nn package, I should say. These are all abstractions of nn.functional. The nice thing is that not only do you get mean squared error loss, you could play around very quickly with different options, right? Without having to go up and do a whole bunch of coding to try to test a different way. So now that we have a loss function, we need an optimizer. And so that's the beauty of the torch.optim package. Basically, we have all sorts of optimizers we can choose from. So the big one that we've been using pretty much constantly throughout this course is gradient descent. Also stochastic gradient descent because it's a variation. We usually define the parameters equal to, we usually randomize the parameters. So stochasticity, gradient descent. So this gradient descent usually computes a gradient over a subset or mini batch of data. We'll go over batching a little bit more later on, but the long and short of it is that previously what we've been doing is calculating the losses for the entire data set. We go through every point in the data set, calculate the losses, and then change the training parameters based off that, right? Which is fine. We've been working with data sets of like tens, couple hundreds at most. Doesn't really affect things. But now imagine your data set has millions and millions of data points, right? If it has millions of data points, it would be stupid to actually calculate the loss for every single data point and then change the gradient based off that. It would A, tax your computer because you would have to store the entire You have to store the entire data set in memory. Not a good thing, especially for some of the larger data sets. Some vision data sets are on the orders of terabytes. It's hard to even download them. You can't really keep them all in memory at once, right? So in order to counteract that, the idea is that you have a large population and you want to determine something about the population. Well, you could go through and do a census, i.e. ask every single member of that population for that piece of information. Or you could get a good subset, 10% of the population, have them fill out the survey, and then be like, a big enough sample size is probably reflective of the population itself, right? So that's what stochastic gradient descent is. That's sort of the idea behind mini batches, is that you just group pieces of data together and calculate the gradient all at once. And you don't have to calculate the gradient for the entire data set. You only calculate the gradient for a subset of the data set, and just sort of assume that whatever you calculated is represented or close enough to what you would have gotten if you included the entire data set. Okay? So we're going to go over that a bit more, especially when we discuss deep nets and the image data sets, because this becomes particularly hard when your data set is large. So that's pretty much when we'll discuss it. But that's the reason why stochastic gradient descent is the way it is. It's because it basically assumes that you don't use the entire data set to calculate the gradients. It assumes that. Safe assumption. Anywhere outside of a learning setting, that's pretty much guaranteed. You won't use the entire data set to calculate the gradients. And it assumes that you calculate the gradient for batches of data at once. Okay? So the pros of this, again, I think I explained. Pros of this is faster than gradient descent because you're not going through the whole data set. Again, standard gradient descent assumes a whole data set. This stochastic gradient descent assumes subsets of the data set. That's what, again, it won't be perfect. There will be some variation, but it's usually good enough. And one of the other pros, the theories behind the pros, is that if you have a stochastic gradient calculation, you ideally won't get stuck in local minima. Is that necessarily always the case? Not really. I don't know. I haven't really found it convincing that stochasticity helps you avoid local minima all that well. I think you usually just want to have different start seeds. That helps you far more. But for some networks, I guess it might help. But the other issue is that, of course, convergence becomes an issue because you're only calculating gradients for subsets of data, and your gradients won't be the same. So it will be hard to converge on a single universal minima, okay? Because there won't be a universal minima because you'll have different minima for different subsets of data. So you'll probably hover close to the universal minima, but you'll just bounce around a lot. Okay. The other useful thing, we discussed momentum. So there are a lot of improvements that you can make to optimization, as we discussed in the primal optimization lecture. So momentum was one of them, right? We have an option. We want to avoid the gradients. We want to avoid the gradient turning on a dime, right? It just hurts us for various reasons that we discussed in that lecture. So having a term that remembers the previous gradients and incorporates the previous gradients into the current gradient calculation, that was useful. So so having momentum is useful, which is included in the standard gradient descent optimizer. There are other useful little things that are included in the optimizer. For instance, having a weight decay is useful in the optimizer because you could because having a weight decay, all the idea behind weight decay is simply to decrease the weights, to decrease the learning rate, the more epochs or the more iterations you do. Okay? That's all the idea, is that the more iterations you do, the closer to you get to the minima anyway. So maybe it's useful that as your program goes on, as you train longer and longer and longer, maybe you should just decrease the learning rate, even if you're not sure you're close to a local minima or not. But the idea is that, but if you're training for a long time and you're still not settled down, maybe it's because you're bouncing around the local minima too much, right? So it usually never hurts to have some form of weight decay. Just have something, just have sort of an upper limit that, you know, I've been training for 100 iterations. I should be close to the minimum right by now. So I'm just going to include a weight decay that sort of decays by a half every 100 iterations. And then eventually, if I keep training it, hopefully that instability that you get from having too large of a learning rate will eventually disappear, right? That's sort of a guarantee, right? Over time, even if there's an instability beginning, it'll eventually disappear if I train long enough. Other improvements, L2 regularization we discussed. There are all sorts of things. You could go through the documentation for hours and discuss all the little optimizer improvements that you can enable. But that's for another day. But the major ones that we discussed are the major ones that people use with stochastic gradient descent are momentum, weight decay, regularization, the different types of regularization, more than just L2, L1, and other types of regularization are often used. And yeah, you could enable this all with stochastic. You could enable this all with the optimizer. That's the usual thing. And the more important thing, and unfortunately I don't think we'll get to it in this course, but there are many other optimizers that are useful, such as Attograd and Atom. So all of these are adaptive gradient methods. Again, similar to weight decay, but they're adjusting the learning rate using other heuristics. Especially Atom is pretty much, I would say that a good, I don't know, 80% of the papers I read pretty much just default to the Atom optimizer. A lot of these are basically based off the same ideas as normal gradient descent, but they have a bunch of other advanced learning methods, advanced heuristics to adjust learning rates and things like that. So there's all sorts of optimizers you could use. Let's actually go in and try to use it, I should say. So for instance, all you need to do to have an optimizer is simply to create an optimizer object. And you create the optimizer object by inputting in the parameters of your model, the learning rate or the initial learning rate. If you're using some sort of weight decay or momentum, these things change. So you have an initial learning rate, you have some momentum value, 3.99. I usually use 3.90, but it's fine. And you have some weight decay values, which should be very small. The weight decay should usually be very small. Don't put like 10 or anything in that. That'll break it. I've done that before. So yeah. Yes?
Do we always have to do it in this order, or like do we always have to reference learning rate as LR, momentum as momentum, and weight decay as weight?
You have to always reference like LR equals. Yeah, okay. LR equals. I don't think actually, this would be, maybe this might be a good break. I'm actually curious to see if there is a default learning rate. SGG, yeah, optimizer. I don't think there is a default learning rate. Okay, I think LR is a required parameter. Yeah, I'm pretty sure. Unless someone correct me if I'm wrong, but I think LR is a required parameter. Momentum and weight decay are not. Yeah, but you should always say LR equals momentum equals. That's one of the things I do approve of in Python. Compared to C and C++, that you can specify the particular inputs. Okay, so learning rate adjustments. how you determine a learning rate, I can't give you a recipe for that. That's one of those things that pretty much you'll just have to experiment and determine for yourself. It's very natural to have a default learning rate you'll always go to, like 1e to the negative 3 is something I always start off with. But really, depending on the data set, depending on the model, these things could change. The best thing you could do is if your loss, if you try learning rate, if your loss isn't converging, try lowering the learning rate. If your loss is going down but very slowly, try raising the learning rate. So you should always try to plot your loss. You should plot your loss and then just look at it and see what's happening, and then you'll learn how to adjust your learning rate. There's no real standard formula for that. Okay, so we have all the necessary components of creating a machine learning model using Torshed NN. So we need to initialize the model. We need to prepare our data set usually. We'll assume now the data set is prepared, and we need to define a loss function in optimizer. We need to create that object also. So create a model, create loss function, create optimizer, make sure data set is prepared, and then with all of these things in hand, we simply zero out the gradients in the optimizer. We pass we either pass the entire data set or a batch of the data set into the model to create predictions. We calculate the loss from the criterion, and then we back propagate and perform a gradient descent update by using optimizer.step. This is a key thing here. Oops. This is a key thing here that basically changes the values of the parameters. And then you should always, I mean, this is optional, but not really. You should log your actual, log your losses just to see. You should at minimum log your loss values just to make sure your model is learning and try to determine if there are options you could change in order to make it learn better. So let's practice with some example data. Namely, we have some data here. We just generate some data. Sorry. We generate some data here. So what are we doing here? We're just generating some arbitrary data. We're having a bunch of positive cases and a bunch of negative cases. We're going to do a classification problem that we've seen in the last two lectures. So instead of using sklearn, we could just use the random function and generate the labels like so. And of course, the data here is centered on 1, -1. The cluster here is centered on 1, -1. The cluster here is centered on -1, 1. With some variation because we're using torch.rand. So that's the data we have, and we want to classify based off of it. Okay? So how do we do that? Well, by the way, these are just helper functions to plot the data and determine the model accuracy. This is actual data right there. Okay. Okay. So we want to actually build a model to classify this data. Come on. Yes. Okay. So how do we do that? Well, we want to build a logistic regression model. We want to build a logistic regression model using the logistic regression class that we built a couple slides ago. Just jump right back to it. Right. Nope, that was too far. There we go. We have this logistic regression model that's literally has all of this. You pass in some dimension to the data, and you get a sigmoidal function for 1 over 1 plus e to the w times x, whatever the number of inputs is, whatever number of x's is, times the number of parameters of w plus b. So we'll use that logistic regression model. And say we have a 2-input model. Makes sense because we have a 2-input model for the data that we're trying to match. So we create that model too, and then we create a particular criteria Namely, we use the binary cross entropy loss. Again, this is literally the same as the function that we've discussed in the prior lectures. And simply, we do the reduction, and we say instead of doing the sum, we'll do the mean. It doesn't make a difference between sum and mean. Well, it usually doesn't make a difference. Not for us here. Sometimes it can. But we'll just say we want the reduction to be the mean of the binary cross entropy loss for all the data points here. And then we define a learning rate, 1e to the negative 2, higher than I would have started with, but that's what lets it work. And then we define an optimizer. Torch the optim, stochastic gradient descent. We give it the actual parameters in the model, and we give it the actual learning rate. Nothing else. Okay? Basically, all the optimizer needs in the beginning is the model parameters and the learning rate. Okay? And so, before we do anything, right, we have the actual objects that we need, but we're not actually changing the parameters or anything. We're simply created a model, right? We created the optimizer and loss function, but we haven't really computed anything yet. So when we actually look to see what the model is predicting right from the start, we see that it's predicting sort of a division that goes from a division between basically negative values of 1 and positive values of 1, right? That makes sense, right? Why does that make sense? It's because if we go back to the actual initial class we defined earlier, wait here, we define this parameter as basically having no bias and positive slope for each of the inputs, right? So if we go back to what the initial guess for the model is, what the initial guess for the classification is, no bias, centered on 0, 0. Oops. Why do you do that? Okay. Centered on 0, 0, and then positive slope, m is equal to 1. Okay? Makes sense, right? So this is our initial guess. Probability of a positive class. This is our initial guess, and our initial guess is pretty terrible. It's pretty god-awful. I'm pretty sure this is the worst possible learning rate we could possibly get. Okay, so how do we train the model? That's the question. How do we train the model? Well, we could use no momentum. So we'll use no momentum, no weight decay, none of the advanced stuff. We'll get to the advanced stuff in a moment. But for now, we just want to train the model and using the very standard accuracy, very standard options, okay? So we have a little piece of code. Now, don't fret. Most of this is plotting. Like 90% of this code is plotting. But the important part is right here, okay? We have the model, we have the criterion, we have the log model, we have the optimizer. Same as we defined before. And so what do? Well, we need to have we need to define the number of iterations we want to go through, and we need to just define how many data points that we'll use, how many data points we'll use for every calculation of the gradient. Okay? We could use the entire data set, or we could use some subset of the data set. It's easier we're using some subset of the data set right now just to demonstrate what you could do. So what do? We zero out the gradient for the optimizer. We take some subset of the input data, and use it to calculate some predictions using the model. Okay? So then, the predictions that we calculate the loss based on the labels that they had in the data set. And then what do? We calculate the backwards propagation. We back propagate, sorry. And then based on the back propagation, we do a step of the optimizer. Okay? So notice that we're not actually giving the optimizer the loss function itself, right? The optimizer doesn't care. what happens when in backpropagate? Remember, there is a grad fn variable. There's a gradient variable with each of the parameters that when you say loss that backward, that variable gets populated, right? That variable gets populated. So what the optimizer sees, we created our optimizer. The optimizer is simply an object with that is simply an object that has a list of parameters that it knows it needs to optimize. And what it sees is that it goes through each of the parameters and it sees the gradient in each of the parameters. And based on the actual gradient in each of the parameters, that numerical value, then it updates the value of those parameters. Okay? So that's actually kind of a clever thing, right? Because we are entirely separating out the loss function with the optimizer. It makes it very, very general because the gradient itself, using the computation graph, is just a number. The optimizer is looking, and all it's looking is at that number, no matter how complex your loss function is. And believe me, it could get very, very complex. You don't need to encode that. You don't need to program that into the optimizer. All the optimizer at the end of the day cares is it sees a couple numbers in the gradient. It sees a couple numbers for gradient, and then it says, okay, based off these numbers, I think I should modify the parameters this way, and I'll modify them that, and then we just go through and do the loop again. Okay, that's the whole point of computation graphs, of defining the loss function separately, of defining the optimizer separately, is to make this as general as possible, as general as possible. This is, I think, one of the reasons that PyTorch is more used than TensorFlow, because TensorFlow does combine these things in a lot of cases. It does combine these things. You don't necessarily have to, but TensorFlow has very nice wrapper functions that allows you to implement a deep network with like only a couple lines of code. That's wonderful. But it also takes away your ability to really mess with the engine. So PyTorch is trying to balance that by saying that, okay, we don't want the coding to be too cumbersome. We don't want you to actually have to implement the gradient at every turn, right? That's the whole point of the computation graphs. But we also don't want you to have to rewrite the optimizer if you decide to use a weird loss function, right? So it separates out these things, and so all you do, zero out the gradients, calculate the predictions, calculate your loss, calculate the gradients, optimize, and just do that for a bunch of iterations, okay? So if you do that, escape. Out of curiosity, nope, not for this one. Okay, that's okay. For the next ones, I was better. Oh. If you do that, you get something that's closer to the classification, right? That's not optimal. So you get something that's closer to the classification. Okay, so something that's much closer to classification, though I will admit this is not necessarily optimal, right? It's close, but I would guess the optimal solution should be more like that, okay? So what do we do in this case? Well, we have to use some more advanced features. So what are the advanced features we could use? I'm sorry. That formatting, weight decay. Hold on, one sec. Yeah, why is this not? Oh, I know why it's up here. Okay. Go back. Oh, yep, okay. Yeah, okay, so we have to use some more advanced features. So what are the more advanced features we can use? Well, the obvious one that we discussed during the primal optimization lecture is momentum. Momentum is a beautiful thing. It seems to always help. I can't think of a case where it didn't help. So why don't we try enabling it, right? So again, instead of rewriting a whole bunch of things, instead of doing a calculation for momentum and everything like I've done in previous lectures, well, we're just using an optimizer, and we'll just tell the optimizer, turn your momentum on, put it at 0.99. That's fine. Just turn it on, okay? So if we compare, we could compare And if we do that, we could look at the two different options. This is without momentum. So again, not the perfect classification, not the worst classification in the world either, but it's not ideal. But then you go and see with momentum how much nicer that classification is. And the model is much, much more sure, right? So logistic regression doesn't have a margin, but you could see that the actual sigmoidal function, the slope is now much greater than the absolute value of the slope is much greater than it is in this case, because you see that transition area is much smaller. Okay, and also. Also, one of the things that's sort of nice or sort of interesting to see is that without momentum, the loss sort of decreases very standardly. With momentum, it's much more chaotic. But with momentum, the decrease is far greater. The decrease is far greater initially, and then it sort of starts oscillating here. Without momentum, the decrease is very gradual. Okay? So I'm sure if we ran more iterations, we might be able to get a better classification. But momentum gives us a good classification and very few iterations already, right? So why not use it? Okay? So there are other options that you could use. For instance, you could use the weight decay. Boom, 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 boom. You could use weight decay. So again, we use momentum. We have momentum now, and then we can now, with momentum, we'll turn on the weight decay. We'll turn on weight decay, see how that changes things. So all we need to do to turn on weight decay, again, we just initialize the weight decay variable. So let's see, we turn it on, and then we get this, okay? So with weight decay, the loss actually I would say the loss function improves. The loss improves, it becomes more stable, and actually the accuracy goes and becomes more stable. But you get sort of a loss of certainty of the classification with weight decay, which actually might not necessarily be wrong, because you have values here, you have values on both sides. So maybe you don't want the slope to be so great. It's hard to know what exactly the perfect answer is. Both of these relax to almost the same accuracy, although this accuracy is slightly higher with weight decay. So if accuracy is your only goal, great, but might not be your only goal. Either way, weight decay does change things. So could we improve this even better? Well, we could. So we could vary the momentum. Actually, we did this. We just vary the learning rate. I think that's the, what was this? Learning rate.
On the side, do you have a weight decay?
I have weight decay, yeah. We went over to weight decay. I think this was just for varying the training parameters. This is just a exercise to vary the momentum. So instead of choosing 0.99, you could choose anything. So for instance, 0.5, and did it actually go? There you go. Oh man, Jupyter Notebook is killing me. Well, you guys could play with this at home also. The major thing to consider is that doing the things this way, it just makes things a lot easier. Okay, so feel free to go through, change the learning rate, change the actual other parameters, momentum, weight decay. L2 you could try L2 regularization, although I'm pretty sure in this case it won't. I'm pretty sure it will make things a lot worse in this case, but feel free to experiment with that. And so that's good. the one thing, oh, I remember why. So the one thing I will say is that this isn't ideal. And so a lot of the reason for this stochasticity is the fact that we chose little subsets of the data, right? When we choose little subsets of the data, the calculated gradient is going to be different every time. And so you're going to get sort of this, this randomized pattern, which I would like to point out is not the worst thing in the world because we are dealing with very small changes in loss. This is a log plot, right? So this sort of, this jump is basically, it's jumping between 0.1 and 0, okay? So not that bad. But the only hard thing is that over here, we had to do a lot of work to actually gather those little subsets of the data, okay? So this work to prepare the data set and stuff, even that's too much work for us. Well, it's not too much work, but it would be nice if there was a library to do all of this for us. And that's what we'll discuss on Tuesday, okay? Okay, so that I think is it for today. Have a good weekend. Homework 5 is due Monday. And then we'll talk about PyTorch data management on Tuesday. And yeah, just have a good weekend. Enjoy the nice weather while it lasts. All right, thank you guys.